Again, welcome. Today is October 22nd. We are right around the middle of the semester. We just passed basically the other half, and we're working toward the second exam. The thing to be aware of is the fact that I have posted a homework that I promised. Actually, I should have posted it early this week, but I didn't. Anyway, it's on Canvas. It's actually on, I think, the week after the exam, which is last week. Let me double check to make sure I give you the correct information. So this is Physics 10. Let me go to models. But you should have been notified by Canvas that you have that assignment. But I just want to remind you, it's actually week 9. I mean, this week. I posted on this week. So it's immediately after this discussion, the assignment for the homework. But the homework is actually the previous chapters. I think chapter 15 and 16 or something like that. One of the problems we did in class together. At least one, probably more, okay? So I just want to take your attention to that thing so that you guys don't miss on that homework. It has 6 problems basically from 2 different chapters. And again, if you have any difficulty, please let me know. Do not struggle with it on your own. Let me know. We can meet. We can sit down together basically on Canvas. And if it benefits everybody, I'm going to record it and post it so that everybody else will take advantage of it and complete your assignment. It should not really take you too long. If you find yourself spending more than an hour actually on the entire homework, you know that it's not right. You need to let me know and we work on it. Does this make sense to you guys? Yes or no? Okay, very good. I really appreciate that you guys let me know. The only thing is that I warn you about that is do not expect if you let me know, let's say for example, now that within the next hour that I'm going to be available, especially on the weekends, because during sometimes I'm teaching, sometimes I'm meetings, and sometimes I really need to get near a computer. So let me know ahead of time, hey, I'm struggling with this question from this page. Can you help me with it? Then we set a time when we meet and then we meet on it. And if it's a quick thing, it's a quick thing. If not, then we work it out together. Okay? So I really don't want you to struggle through that. I want you to understand that that's the main thing. The other thing also, for any homework assignment, you are highly encouraged to work with your peers or with any other resource, as a matter of fact, that the purpose of which is not to challenge you and basically keep you guessing. No, actually, it's to work yourself through it so that you understand how that worked out. Okay? So that's the whole purpose of this, hopefully. And I think I made it clear also in the assignment itself. Okay. So let's jump into the chapter. Today we're finishing thermodynamics. Actually, this is a summary. I know we mentioned a lot of these things that are in this chapter, but we're going to basically put it together. Okay. This book skips on a very important law. Actually, I have the author for 2 different classes with 2 different books, and he apparently skips the same law, which is the zeroth law of thermodynamics. And in the summary, as I give you every chapter, I give you the summary of it, and along with the basically the PowerPoints and things like that. I made sure that the zeroth law is mentioned in there. So again, historically, this science of thermodynamics, the part that we're doing right now, has been discovered backward. It was the second law was discovered first, and then the first law was discovered second, basically, or at least was stated second. It was not discovered. The conservation of energy was a known thing way before these things. But when formulating this science, they realized that the question that Mr. Carnot has asked actually should be second after the conservation of energy, which is a really big, more fundamental principle, and not just in physics, apparently, and everywhere. So they thought that that should be first, and it is, okay? Then after a while, where they're putting the foundation for this whole branch of science, which is thermodynamics, which is really rooted. I mean, it was started by an engineer, but it's really physical science, physics actually, and now it has implications everywhere. You cannot do anything without it in other fields, such as, for example, chemistry and biology. And as I mentioned before, it really has went to even other realms. For example, even astronomy has it, and now philosophy and religion, they are all talking about these things that have to do, especially with the second law of thermodynamics. So it's a big law. So when they were putting its foundation, the foundation of this branch of science, they realized that there is actually far more rudimentary concept that we need to have, namely the concept of temperature. How do we measure it? Okay, because it's far more basic than even the law of the first law. The first law basically states that any system, its internal energy is the sum basically of how much was work it does plus or done on it plus the amount of heat that is added or removed from it. So that's basically the entire thing. That's how the internal energy of a system. The internal energy turned out to be proportional to the temperature, to its temperature. So we needed a way of measuring the temperature, and the temperature, we stated the zeroth law. So the zeroth law is really a law to allow us to invent a thermometer, no more. Okay, so that's why we needed it first. Then we can jump into the first law of thermodynamics, as I stated, where the internal energy of a system, we meaning, for example, a gas, is proportional to its temperature. So now we have this connection. So we defined what the temperature is using the zeroth law. Then when we go to the first law, we have a way of talking about that energy and now connecting it to other things like work and heat. Okay. The second law of thermodynamics, which is really the third law in order, okay, state talks about something else, that when we are talking about heat, and if I have two systems sitting at two different temperatures, one of them is sitting at a higher temperature than the other, there is no spontaneous way, there is no automatic way for heat to be extracted from the one that is colder with a lower temperature and be dumped to the one that is higher temperature. You need, I mean, spontaneously by itself. The other way around is okay. The other way around, namely, if I have a system sitting at a higher temperature and a system sitting at a lower temperature, and if I put them together next to one another, heat will automatically transfer from the hotter, the one with the higher temperature, to the one with a lower temperature, and that is the natural process for it. Okay. Now, you ask, how about AC unit? That's exactly what it does. It takes heat from the colder environment and dumps it to the hotter environment. But that is not a natural process. That needs energy. That needs work. Actually, the compressor of the AC unit or the refrigerator has to do the work. So it's not a natural process. What we're talking about is our natural processes. So that is the second law of thermodynamics. So Mr. Carnot actually asked a basic question, and he said that what is the most efficient engine? Today we're going to talk about the efficiency of the engine and Mr. Carnot's basically relationship that he found at the end. And he said, grant me the following, namely the second law of thermodynamics, that heat cannot spontaneously transfer from a system that has a higher temperature to a system that has a less lower temperature spontaneously. Okay. There are so many processes involved in here. One of the processes we're going to learn about it in this chapter is the adiabatic process. This is a process where there is no exchange of heat. For example, I have my cup of water and here it's an icy cold, and that's why I'm enjoying it. If I wrap this one with a blanket, if you wish, and insulate it so that no heat will go into it, or I cannot extract heat from it, this is what I call an adiabatic process. So an adiabatic process really is a process where there is no heat exchange. Sorry, there is no heat. Q is equal to 0. That is what's an adiabatic process. There are other processes that are well known and documented in any textbook of thermodynamics. And we're not going to talk about them, but they are very important. One of the processes that we can talk about is the one where there is no change in volume. This is called an isochoric process or an isovolumetric process. That's a process where the volume does not change. There is another process where the pressure does not change. Delta in here, that means change. the pressure does not change. If the pressure does not change, this is a pressure that is called isobaric process. So this is isobaric. That means the pressure is the same. Iso means the same. Isobaric pressure. This is one word, not two words, okay? So if you play Scrabble, this is a good word for you to remember, okay? Whereas this one is called isochoric or isovolumetric. It's the same thing. Volumetric process, okay? This is the adiabatic process, okay? So these are three examples of three different processes. And there is a very, very important process that is used, especially in refrigerators, and it's used in heat engines and it's used a lot. And that process is actually called the isothermal process. This is a process where the temperature stays the same, does not change. So iso means the same. Thermal, in this case, we're talking about the no change in temperature. Temperature is the same, okay? So imagine, for example, you have a gas that is expanding so rapidly and it's in contact with a heat sink, which is, for example, the environment, okay? Dumping its heat to the environment where the temperature doesn't change of the environment just because somebody is dumping heat to it. Like the refrigerator, for example, it dumps heat to the outside. The outside is so big and large that it does not impact its temperature in general. Unless you put the refrigerator in a very small containment, then it will impact its temperature. And at that time, it's not an isothermal process. It's a process that involves changing temperature. So these are some of the famous processes. When we talk about the second law, really, these are the two main processes for us, at least in terms of Mr. Carnot. Okay? So these are the main processes. So the adiabatic process is a process where there is no change in heat. Think of it as you take your system and you wrap it around in a big blanket, okay? So that there is no change in heat, okay? Or no change in heat. Versus something that where the temperature doesn't change. There is an exchange of heat. For example, when a gas expands, for example, coming from the refrigerator unit, it's actually temperature is changing, okay? But it's doing it. I mean, not temperature. I'm sorry. Its heat is changing. It's dumping heat outside. But in that point, since it's in contact with the environment outside, there is no heat in there, or at least no significant heat, no significant temperature change. Okay. So this is in a nutshell what everything is. We'll talk at the end, toward the end, about the entropy. The entropy is a concept related to the second law of thermodynamics, and it's related to also the order and the disorder, okay? And this is really what's going on in the case of temperature, why it will not go spontaneously from the hot source to the cold source is because the entropy needs to increase, okay? And the only way for the entropy to increase is for the heat to go from the hotter to from the one with a higher temperature to the one with a lower temperature. We have to be specific in here in terminology. So this is in a nutshell what this chapter is. And the concept of the entropy itself is the one that took so many dimensions now. This is the concept of entropy that now has entered even the realms of philosophy and religion. And there is a big debate between people who believe and don't believe, and Penrose is very much involved with that, and everybody else is talking about it. I really don't agree. I mean, look, in physics, personally, my personal belief is the following. Where experiments stop, where we cannot do any more experiments and observations, that's where we should stop, and we basically should technically shut up. We don't really have anything to say as physicists. I mean, your personal views as a human being, yes, you have your views and faith and belief, that's fine. But at that point, you stepped up in the realm of metaphysics, which is not really related to physics, so you're talking nonsense. So that's basically the belief I have. And some of you might already, at least those who read enough, the laws that are coming up right now with the so-called string theory. So string theory is actually also may also fall very well be in the metaphysics at this point because we cannot do any experiments with it. Okay, so the science of thermodynamics was developed in the early 1900s. Mr. Carnot asked the question in 1824, to be specific. So that's more or less the date when it was initially started. But formulated later on in the 1830s and 1840s. Okay, so that's where this branch was there. Uh, at that point, we didn't have no idea what the atoms were or molecules were and everything else, but it was actually Mr. Boltzmann who first introduced the need. Sure, is it one N or two N's? I always confuse his name with somebody else. Yeah, it's two N's. Okay. Who first introduced the idea in order to understand PV equal to nRT, which is the foundation where this science really is based for an ideal gas. He introduced the concept of tiny particles in the air. And of course, people made a lot of fun of him, at least at that time, since they didn't know whether atoms existed or molecules existed. And that led to tremendous pressure, according to some basically historians. That's why he committed suicide. That's why he killed himself. Nowadays, when people go, and he's actually the one who introduced this concept of entropy at the end. And there is a famous formula for that bears his name actually for the entropy, and the entropy is constant now, the constant that is related to this R, which is called Boltzmann constant. And it's a very important stuff that he did. So physicists nowadays, when they go to Vienna, where he's buried, they go actually and visit his tomb because to honor him and the things he did and recognize the fact that they did him wrong, or at least people at his time did him wrong. Again, I talked about the conservation of energy and the fact that hot or heat does not flow spontaneously from cold to hot. It always spontaneously goes from hot to cold, okay, and not the other way around. So those are the two principles, really, okay. As I said before, there is another principle in here that the author is always skipping in this textbook, and I really want you to understand too and have it there, and that is this concept of thermal equilibrium. System A is in thermal equilibrium with system B. So this is thermal equilibrium. And system A also is in thermal equilibrium with system C. That means that from these two propositions, or this whole proposition, that implies that system A, system B, is also in thermal equilibrium with system C. This allows me to invent thermometer, and the thermometer in this case could be my system A. Okay, I gauge A, for example, with water, and I know when the water boils and I know when the water freezes. At that point, I'm going to call the temperature of boiling whatever, like 100 degrees Celsius, for example, or 200 or 212 degree Fahrenheit, whichever unit you like to call it, it's fine. And then you know where it's going to freeze. You call it, for example, 32 degrees Fahrenheit, or you call it 0 degrees Celsius, and you're going to graduate the table in there, going from 0 to 100 or from 32 to 212. And then each time you jump from there, you know how the water behaves. You take this as compared to water, and now you put it with another substance other than water, like the room right now we're in it, and it reads, for example, 79 Fahrenheit. This 70°9 Fahrenheit is really as compared to when we did the experiment on the water. So in this case, the thermometer is system A. We compared it to water, and now we compared it to the room. So I can say that the room and the water are actually having this temperature of 79, which is right now. So this is how this principle is needed to invent really a thermometer. That is the essence behind it. So that is the principle that is missing in this textbook, and I added it to make sure that you guys have a complete picture, okay? So again, the concept of absolute zero temperature, when people were experimenting with it, this picture is kind of a little bit misleading because you cannot really have technically a zero temperature, 0 Kelvin, and you cannot have really a zero volume. And I think the book also mentions the fact that this is the lowest possible and it is not attainable in a sense. So what people were doing at that time, they were experimenting with different gases with different concentrations at different temperature. This is where the water freezes, and when you increase the temperature, for example, the pressure increases. Okay, so you lower the temperature below zero, and sure enough, the pressure decreases also with it. So the experiment that they were doing, for example, there are two experiments. This is one of them. The pressure and the temperature, they go hand in hand. Or if you wish, if you keep the pressure the same, you can have the volume. So this could be the volume. Okay, the volume also is decreasing. If you keep on doing this, of course, at that time we were limited in terms of how much pressure, how much temperature we can go below zero. But it seems like all the curves for different gases, if I extend them, they meet in the same point. And that point is when the pressure drops to zero or where the volume drops to zero. Okay? So this temperature happened to be negative 273 degrees Celsius. To be specific, it's negative 273.13 or something like that. But the point being in here, this is first of all a theoretical limit. We cannot reach it experimentally. Okay, so this is a very, very theoretical limit, because when I extrapolate these lines, they meet, all of them, they meet in the same point. At that point, that is when theoretically the pressure drops to zero. The reason why we cannot really do it in laboratory at all is because when we are at very low temperatures, we want every motion to come to a standstill so that the pressure drops to zero, because the pressure is related to how much the agitation there is there. So if you technically drop the pressure to that level, at that point there is no more motion. Everything comes to a standstill. The atoms will basically come to their rest. And that is not possible, because at that point there is a quantum effect where quantum mechanics takes over, and basically the gas will stay in motion. That's why you cannot do it in a laboratory. There is no way you're going to have this stop completely. So it's a theoretical limit. I mean, we can reach within the 1 Kelvin or even below that, fractions of that, I think. I don't know if we have done it at all, but we can reach very low temperatures, but we cannot get to zero. It's impossible to get to zero, okay? So this is one thing that we are basically, we know is. So 100, this is basically the lowest temperature that you can have. So that's how it was discovered. So instead of measuring things in degrees Celsius, people shifted the whole scale into kelvins. We know we cannot have this region at all. You cannot have a negative temperature below 0 Kelvin. So then everything is shifted this way. So the temperature in Kelvin is the same temperature in degrees Celsius added to it 273. So if you know that the gas, the water freezes at 100 degrees Celsius, freezes at 0 degrees Celsius, then in this case, it's equivalent to 273 Kelvin. It boils at 100 degrees Celsius. That means its temperature when it boils is 373 Kelvin. So this is the temperature where the water basically boils. We are sitting right now at room temperature, which is about 27 degrees. Okay, 27 degrees added to 200. Actually, right now it's probably a little less than that, but on average, anywhere between 293 to 300 Kelvin is what is known as room temperature, where we are comfortable. Okay. I think I don't know if we're going to do a lot of astronomy in this class or not, but down the road, one of the things that we look for when we're exploring other exoplanets is their surface temperature. And we want an average temperature to be around this temperature, at least for a human basically comfort. So this is the temperature that we look for. when we're exploring other planets. Okay. Anyway, so this is basically how thermometers work, and this is related to the zeroth law of thermodynamics, actually, because now we have scales. We can use the degree Celsius or the Kelvin, or somebody else uses also the degree Fahrenheit. Here is the first question of the day, okay? Or actually, the note of the day, if you want, the point of the discussion. When it comes to Fahrenheit, when it comes to Celsius, there is also the Rankine, I think, or is it called the other scale? Okay, is it the Rankine or what is it called? I guess in here. There is also another one. So this is not popular. So ignore it for right now. So let's just focus on the ones that we know on the daily basis. So we use the word degree next to them. We append this tiny zero to them. Okay. Whereas when it comes to Kelvin, we don't do that. So Kelvin is treated as a unit. Okay. It's not listed in the MKSA system. MKSA as the SI units, but it's understood to be one of them. So the K in here is actually referring to the kilogram. So let me type the question so that everybody is on board, so that we are at least the prompt. So we append. Oh no, I don't want to do that. I want you guys to type it with your own words. Okay. So we append the degree when we're talking about Fahrenheit and Celsius. Okay. We don't do that to the Kelvin. We treat it as if it's a unit, okay? So we don't do degree Kelvin. Although sometimes you may hear me say degree Kelvin. That is a mistake, okay? It's not, it's like a verbal mistake, okay? But you will not see me type it. I will not do that mistake, okay? But I don't think I catch myself before doing that, okay? So you need to resist that temptation. So we say the degree Celsius, the degree Kelvin, I already said it, okay? The degree Celsius and the degree Fahrenheit, but we don't say the degree Kelvin. We treat it as a unit, although it's not part of the MKSA system. I mean, it's not put in there, but it works with them too. MKSA, and that is meter, second, kilogram first, kilogram, second, and ampere. Those are the fundamental units that we use, okay? So the K there is not the Kelvin. Yes? Did everybody catch the prompt for today? Yes or no? Okay, very good. At least one person responded. Isaac also, very good. So let's continue. Internal energy, I already stated the fact that this is the energy at the level, at the particle level within a substance in several forms, which is taken as the whole thing as the internal energy. The internal is quite complicated. The simplest forms are, of course, kinetic and potential energies. So this is usually a simplification of all of those things. Remember, at that time, we didn't know that the atoms exist, so we cannot really talk about their kinetic energy or potential energies. Okay. But our studies focus not on the internal, but also on the change of the internal energy. Okay. The internal energy, where the symbol for it is U sometimes. This is the internal energy. This is a state variable, meaning every gas at any given point in time, it has a given pressure, it has a given volume, it has a given temperature, it has a given number of moles actually, and also it has a given energy. So this is a state variable. But when we calculate, we really don't care about this energy itself. We care only about the change in energy. So what matters is the change in energy, in internal energy. So we usually don't know what it is and we don't care. Okay. What matters in this case is how much did it go up and down. Okay. And that's what the first law of thermodynamics talks about. That the internal energy is really, I know that it says in here, heat added to a system, increase in internal energy or plus work done by the system. So it's related to the heat and so the internal energy in here, or the change in the internal energy, is the amount of heat plus the work that the system does. Okay, or is done on the system. So this is done on it, added to it, heat added plus work done on it, then this will be the increase in internal energy. Okay, so that is really what the first law says. If you do work on a gas, for example, compress it, its internal energy will increase. If you dump heat to it, you don't have to compress it, keep it without changing its volume, namely isovolumetric process. In that case, keep it the same volume, but just add heat to it, okay? Then its internal energy will increase. What happens if you extract heat from it? Then its internal energy will go down, okay? What happens if the gas actually does work, expands? Then in this case, its actually internal energy is decreased, okay? So the increase in the internal energy of a system is equal to the sum of the heat added and the work done on the gas itself or on the system itself, okay? And this is an algebraic process, meaning that if the gas does work on something else or the system does work, where is it going to get that energy from to do work? It has to take it from its internal system, okay? In order for a system to do work against the outside environment, it has to take that energy from its internal energies, hence its internal energy will go down. If it does not do work, but somehow you extract heat from it, heat is being extracted from it, where is that heat, which is energy, coming from? It's coming from its internal energy. So I hope that you guys understand what the first law is saying, really. The first law is saying is that energy can neither be created nor destroyed. That is a general principle everywhere. But the idea in here is very specific to this thing, okay? You have a system, A or B, it doesn't matter, cup of coffee, cup of water right now, it's being warmed up right now, all of the ice melted. So you have water in this case sitting at certain temperature, but now in this case, in my cup in here, it has seen heat added to it. Initially, it had ice in it, all the ice melted, and now if I wait a little longer, this water actually will become warm to the, basically going to be a room temperature warm. Okay, you see here the thing that formed on it because it's colder, okay? So it's the heat is being added to it continuously. So later on, if I measure its temperature right now, earlier it was around 0 degrees Celsius because of the fact that it has frozen water, which was ice. Now its temperature is going to reach room temperature, which is probably sitting around 26 or 27 degrees Celsius at this point in the day. Now, it went up by 27 degrees, 27 Kelvin, same thing. Now, its energy must have increased internally because initially it was sitting at a lower temperature. Now it's at a higher temperature. So its energy internally increased. Where did it get that energy? It got it from the heat that was dumped to it by the room itself, by this big room where I am sitting. Okay? So that is the first law of thermodynamics in its glory. Okay? So the first law of thermodynamics talks about the internal energy of a system and the fact that if the system internal energy increases, it's either it received heat from somewhere else, or it had work done on it, or it had both. Okay? Or a combination of the two. In other words, it had heat added to it, But also it could have done work against the environment, but the net heat was more than the work it did, to result in the fact that its energy has increased at the end of the day. Now, if its energy has decreased, one of these things could have happened. If its energy has decreased, we could have extracted heat from it. If, for example, this one right now it's sitting at probably 10, 12 degrees Celsius, if I come later on and I find its temperature has went down, that means its energy went down. So it must have had heat extracted from it, or did work against the environment, expanded, okay? Or both. It could have done both. Had either work done, did work against the environment, or had heat extracted from it and dumped to the environment in the same time, or did both actually, but not necessarily in the same direction, meaning it could have had done work against the environment, but in the same time heat added to it, but it did more work than the heat added, resulting in less energy in it. Or it could have been extracted heat from it far more than the work that was done on it, resulting in a net loss of total energy. Okay, so there are four possibilities for it. Either when we're talking about increase, both of these two are positive, or one of them is positive and the other one is negative, and the positive is greater than the negative. That is if in case the energy is added. If in case the energy is removed, then either both of them are negative, or at least one of them is negative and the other one is positive, with the negative being higher than the positive. Okay, so this is the possibilities in here, and this is really the first law of thermodynamics in its glory. Okay, remember at that time we really didn't know what internal energy was. It took Mr. Boltzmann a lot of work to relate it to the temperature and the kinetic energy for at least gases. Okay, for at least gases. Mr. Joule actually did an experiment where he actually found what is the work, how is work, which is the energy, and heat are related to one another. And he found this interesting result that each calorie, I was going to write on the screen, one tiny calorie is equal to 4.18 joules. I mean, at that time, nobody called it after him. He did a lot of work in this area, but it was called afterwards after his name. So the J in here stands for joules. Okay. So basically, by noting that if he drops this masses, what they do in this case, they take this cylinder and they spin it. When it spins, it agitates the water, and when it agitates the water, now the water is moving higher and higher with higher and higher velocities. And in doing so, the thermometer will, the temperature of the thermometer will show an increase in the temperature of the liquid. Well, he knows how to he knew how to calculate the heat. He knew at least that the heat added in this case is the mass of the water times C of the water, which is 1, times the change in temperature, which he can measure with the thermometer. So the thermometer, based on the 0th law, can give him delta T. C is equal to 1 calorie per gram per degree Celsius. Mass of the water is whatever he put in here. Okay, he knows that. This is the heat, so he knows how many calories were added in here based on the thermometer reading. He knows how many joules these two guys fall. 2. Okay, remember, the height this mass falls into is this mass times g times this height. The same thing, the other mass. So all he has to do is add the two masses, m1 and m2, and multiply them by g and h. And he found that there is connection between the two. And this is a connection. Because this quantity is in calories. This quantities is actually at that time was in a Newton meter squared per second squared. So he knew how many Newton squared per meter squared need to go to balance the calories, and this is the formula. At the end, the Newton squared meter squared, Newton meter squared per second squared was called after him, which now bears his name, Joule. Okay, so that's how we found the connection between the two. As a matter of fact, heat is also another form of energy. I mentioned the state of variables area earlier. that these guys are state of variables. Q and W are not. Work and heat are not. These are transitions. These are things a gas either do or have it done on it, okay, or extracted from it and added to it. It's not a property of a system while sitting at a specific point in space with a specific temperature and so on and so forth. So when work is done on a system, for example, compressing air in a tire pump, the temperature of the system, here is the guiding principle that you're going to be working with in all of these things, okay? So in this case, when the work is done, okay, by compressing, okay, so think about it now. So we have work done on the system. So in this case, the energy will increase. Remember, the change in the energy is equal. So this is not the one. It's the previous one. I'm sorry. Q plus W. So in this case, Q is the same, but the work is done on the system. So it's gone up. So we do work on it. So the energy will increase. And I mentioned already that the energy and the temperature are connected. So if the energy increases, the temperature also will increase. Does this make sense to you guys? Let's go back into this law. Which one? This one. I said that when you do work on a gas, you add to its energy. When you add heat to it, you add to its internal energy. And the heat, and the temperature and the internal energy are proportional. Okay? So in this case, we added energy to the system. When we added energy to its system, we added to its internal energy. In doing so, its temperature must have increased. Okay, I'm glad some people have that. It's all the first law of thermodynamics. Okay, an adiabatic process is the process where there is no heat exchange. Okay, Q is equal to 0. And that is thermally insulated. Use a blanket if you like. I mean, blankets are not perfect insulators. Maybe thermos, okay? Performing the process so rapidly that heat has no time to enter or leave. That is another way of doing it also adiabatically. Adiabatic process is that when you do it so fast, you don't allow for heat to occur. So this is an adiabatic process in this case. So when we add pressure in this case, when we add work in this case, remember, we're pushing, okay, to the gas. So we're pushing it in this case. So what will happen in this case, the process does not involve any kind, we don't need heat to be added in here. There is no furnace in here next to it. That's all the work added to the system. In this case, delta U is equal to 0 plus the work, and the work is positive because it's being added to the system. In this case, the internal energy will increase, which means that also the temperature also will increase, okay? I want you to do this, guys. I really want you, okay? So when you blow on your hand, and when you have your lips puckered next to one another, you will feel difference in this case. So what has to do with it? The air is expanding in the second case, okay? The air is expanding. When it expands, in this case, it's doing work. What happened to my pen? It's doing work against the environment, okay? So when the air is expanding, it's pushing the environment basically around, okay? So when you have your lips close to one another, it's pushing the air around it. When it pushes the air around it, its internal energy now is going to go down because it's doing work. So the work it's doing against the environment. So it's losing energy. And when it loses energy, its temperature go down. Did everybody try this experiment? So you blow, and at that point, what happens is the air will come with the temperature of your internal body, right, and hits your hand, and you feel it exactly how much it is. Okay, it's warm. But when you bring your lips closer to one another, you will feel it colder. Why is it colder? It's because now it's coming, and here when you blow it, it's not expanding or compressing. So there is you feel exactly the internal temperature of the air that is coming from your mouth. But when you have your lips basically closer and you're trying to blow as much air as possible, then in this case, when it comes out, it expands because it comes through a pressure. Now it's going to expand to the room pressure. When it expands, it does work against the environment. It pushes the air in the room next to you. Okay, it tries to even push your hand. Okay, resulting in work being done by the gas that is fast expanding in this case, and that lowers its energy and internal energy, meaning its temperature will go down, and that's what you feel in your hand. Okay. Who tried it? Isaac, you tried it? Samantha? Kyle? Okay, very good. So basically, this is something that you do it intuitively. I mean, in a hot day or in a cold day, you do it actually the whole way around. But that's we'll talk about the other process, but that's basically, but you understand the physics behind it now. The physics is that the gas, when it expands, and that's exactly what comes out of also the pressure cooker too. It comes in so hot. Okay. Okay. Man, I like the coffee when it's a little bit not too hot, but I like it hot. I don't want to blow on it to make it. I'm commenting on Kyle's note about the coffee in here. So the same thing when if you open the pressure cooker, immediately there is tremendous temperature inside, tremendous energy actually inside. So what happened in this case, the gas when it escapes actually will be so hot. But when it expands rapidly, in this case, it's doing against the environment and it's going to cool down. If you feel it, you're going to see it hot and but lower in the top. Don't try this one at home because it's going to burn your hand. Okay. Did anybody experience with the pressure cooker? No? Okay. Thermodynamics is useful to meteorologists when analyzing weather. It's useful for everybody. As a matter of fact, the second law will dictate whether or not a chemical reaction can or cannot happen spontaneously. You need energy to be added to it or not. What do you need to facilitate the chemical reaction? You have to deal with the entropy. Actually, anything cannot happen or happen. It's the second law that governs everything we do on a daily basis. So the first law of thermodynamics is expressed as air temperature rises as heat is added or as pressure is increased. Heat may be added as incoming solar radiation that adds heat, radiation back from the earth, moisture condensation, contact with ground. Okay, this is basically different ways. So the weather can be explained a lot because that's the motion of the mass of the air, and that is basically how the weather phenomenon is governed by the laws of thermodynamics. Again, the air, or at least the cloud, when it rises, again in here, the ground, let's say, for example, room temperature, which is 25 degrees Celsius, as you rise every 1 kilometer, the temperature drops by 5 degrees, by 10 degrees, I'm sorry. And in doing so, the air needs to expand in this case, expands, and that's how the temperature is actually going down. Because in this case, it was a certain volume. When it changes volumes, remember, when it increases, it's going to do work against the environment. And when it does work against its environment, its internal energy will go down and its temperature will go down with it. Okay, so that's how you can how the weather is. It will going to reach a certain point in equilibrium where it does not expand anymore because at that point there is no change in temperature, and that is where we're going to step. Okay. Again, this is the Chinook wind. That's how it's formed. Again, when it rises around the mountains. Okay, it talks about the temperature inversion in this case when the wind blows from the high deserts to the low ends. Okay. Okay, let's read this question. If a parcel of air in a dry initially at 10 degrees Celsius at ground level expands adiabatically while flowing upward alongside a mountain vertical distance 5 kilometers. 5 kilometers, what will be its temperature be? So each kilometer, okay, negative 40 degrees. Okay, these things are really, these are based on observation and experimental laws with the meteorology. This is not something that I'm going to focus on honestly in my class in here, because we're trying to get into the physics part of it, okay? Anyway, the second law of thermodynamics, so that question is, I'm going to skip it for right now. So the second law of thermodynamics is the law that is the started it all, basically. And heat itself never spontaneously flows from a cold object to a hot substance. Okay. In other words, if you take a cup of water that is super cold, heat will automatically flow from the environment that is in towards it to increase temperature. You cannot have the other way around. Okay. So this is the temperature that is hot, and this is the temperature that is cold. Spontaneously, heat will move in this direction. Okay, so this is by itself. This is how this works. By itself, it moves in this direction. In summer, heat flows from the hot air outside into the cooler in interior, and in the winter, it's the opposite. Okay, so wherever you see that, that's how this is. This is spontaneously. A heat engine does the same thing. A heat engine, what it does is it takes heat. This is, for example, in the case of the, oops, what did I? A heat engine, for example, the ones were similar to the refrigerator, for example. A refrigerator is not an engine, it's actually a reverse engine. But an engine, for example, for that works on the principle of heat, takes heat from the hot source, delivers work to you. So this is the heat it takes from the hot source and dumps heat to the cold source. Let's try to explain how this works, okay? Your car engine, for example, so this is work. Your car engine, for example, you have where the cylinders are, okay? In the cylinder itself, where the piston goes in and out, there is a chemical reaction that happens in there. During the chemical reaction, there is a huge explosion and temperature rises so high. So that is your T hot. Okay, obviously it's going to expand. It expands so rapidly. Okay, in doing so, it's going to turn the flywheel with it, which is going to turn some gears, and the gears will turn the tires, and the car now starts to move. So basically, it did work because the car now is moving. And then when the gas is expanded so much, the exhaust comes from the pipe so hot, it dumps that heat mainly, which is CO2, which is carbon dioxide and water, to the environment. So that is because the outside environment usually it's colder, than the engine, and that is mainly how heat engines work. Provided that this is not typically a heat engine because you have some electrical parts in it, but this is how an engine works in general. Okay, it takes that expansion, so rapid expansion due to the extreme heat, and then does work for you and gets you the cold in here. So how much efficient an engine is how much work do you really get out of it versus how much heat you need to get that work done. So that's how the efficiency of an engine is. A refrigerator, though, is the opposite process. A refrigerator, what it does is, this is the cold source. It's still T cold, where the temperature is cold. This is, for example, your meat in the freezer. Okay, this is the hot outside. This is the heat that is outside. Okay, so what it does is it takes work from the compressor, from the engine, from the motor. Okay, it takes so much heat from the cold this way. So this is going to borrow heat from there and add it to this one and dump the outside through the compressor on the back of the refrigerator. So this is actually the opposite of the engine is. So this is how they work. This is called heat engines on the reverse, or heat pump in this case, because you're pumping heat from the cold source to the cold source, to the hot source. Okay, so this is basically how heat engines work. So a heat engine is any device that converts internal energy into mechanical energy, named the motion. The basic idea behind a heat engine is that mechanical work can be obtained only when heat flows from a high temperature to a low temperature. Namely, this is why an engine is. It works based on the second law of thermodynamics. Okay. In every heat engine, only some of the heat can be transferred into work. In other words, not all of the heat is transferred to work. Some of it will be dumped to the cold source. You cannot have a situation where all of the heat is going to work. So in other words, this will never be equal to zero. If it is exactly equal to zero, then the efficiency in here will be 100%. Okay, will be 100%. And there is no such a thing of an engine that is 100% efficient. Here is the story of thermodynamics. It's a kind of depressing story, really. Okay, you need to summarize in the following two processes, two statements. The first law of thermodynamics says the following: because you cannot have energy out of nothing, energy is conserved. So the first law says basically the best thing you can do in any process is to break even. The output energy must be equal to the input energy at best scenarios. Okay, that is what the first law is saying. The best case scenario for your engine is that you break even. In other words, you take 100 joules and you get out of them 100 joules. That is your best case scenario. That's what the first law is saying. Okay. The second law is saying that is not even possible. You cannot break even. If you take 100 joules from a hot source, you cannot get 100 joules of work. You're going to need to dump some of that 100 joules that you took from the hot source to the outside environment. In other words, the work you're going to get is less than 100 joules. You guys understand the story behind thermodynamics? That's the second point of the discussion. Thermodynamics can be summarized in the following two statements. The first law says the best way, the best case scenario is you break even. That is what the first law is saying. The best hope for you is to end up with an even thing because of conservation of energy. Okay? The second law says that is not possible. You cannot break even. You are all going to lose some of the energy to the environment. Do you understand the second prompt of the discussion today? Yes? Okay, very good. So put it in your own words. The first law is the conservation of energy. The most you can do is break even. The second law of thermodynamics really says you cannot do that. You're not going to break even. You're going to always lose. Okay. How are we doing on time? Oh man, well, it's already 5 o'clock. No problem. We can finish this. How many slides we have left? We have about 10 slides left. Okay. Heat engine is okay. We talked about this one. So this is what I was picturing to you, what I was showing you earlier, okay? You take energy from the high source, the high temperature region, you do work, and some of that energy is actually dumped to the cold source. An AC unit is a reverse process. You take heat, you get work from the compressor, for example, and you take heat from the low temperature, and you dump the heat to the outside environment, which is colder, which is hotter, I'm sorry, okay? So that can be reversed, but you can take still heat from the low temperature and put it in the high temperature, but not spontaneously. You have to do work to get that, to achieve that. So when work is done by a heat engine operating between two temperatures, T hot and T cold, only some of the input from the T hot can be converted to work, and the rest is expelled at T cold. That is basically, in a nutshell, what I summarized earlier to you guys. Here is the efficiency of an ideal engine. You need this expression for your homework stuff. Okay, so T hot. You remember T hot is always the higher of the two, minus T cold over T hot, and this number is going to be 1 minus, when you come in the same denominator, T cold over T hot. And this number is always less than 1. Obviously, if you multiply it by 100, it's going to be a percentage, because this is a fraction, less than 1. It's not going to even be equal to 1. It's always going to be less than 1. Ideally, if the first law was the only thing in town, this could be equal to 1. It's not. It's always less than 1 because of the second law. Okay. So a heat engine, for example, and this is called the Carnot cycle. This is really the Carnot cycle is special kind of cycle where the engine goes through 4 cycles. The first one is an isothermal at constant temperature. The second one is an adiabatic expansion, basically, and with no heat exchange. The second one is a compression at the same temperature, at lower temperature, and at constant temperature. So it's an isothermal compression. And the fourth cycle is going to be a compression again, but with no heat exchange. And that is the one that brings you back to the original, hence it's a cycle. There is something called the PV diagram. On a PV diagram, this is an expansion at constant temperature, then a rapid expansion again. In this 2 cycle, it's doing work against the environment. That is actually what you want it to do work. So this is an adiabatic process, and then it's going to compress again at constant temperature with a lower temperature. So this is your T cold, and this is your T hot. Okay, so this is again at constant temperature, and then it's going to compress again back to the starting point with no heat exchange. So these two are adiabatic processes. This is isothermal processes. And at the end, this is actually where the work is. So that is the network of your engine, okay? And its efficiency is given by this expression. This is the T hot, this is T cold, and 1 minus T cold over T hot gives you how efficient this engine is, how much really work you needed to get this much heat dumped into it. And this is where it dumps the heat to the environment, because there is no heat exchange here and there. So during the first isothermal expansion, it gets heat from the hot source. During the second isothermal compression, it dumps heat to the cold source. And this is basically the difference between them is the actual work that it does. Remember that diagram that I showed earlier, that this is the heat taken and this is the heat dumped, and this is the difference between them, the actual network that you get from it. So this is basically how an engine works. A refrigerator or a heat pump works the opposite. Namely, an AC unit works the opposite to this one. The cycle, you do it backward. You go this way and that way and that way and this way. Whereas this one, you go in this direction. So what is the ideal efficiency of a heat engine that is operating between a reservoir of 400 Kelvin and cold sink at 300 Kelvin? It's going to be 400 minus 300 divided by 400. 400 minus 300 is 100 divided by 400. The zeros cancel, and it's going to be 1/4, and the correct answer should be A. Okay. Now, in a natural process, the quality of high quality tends to transform into lower energies, or order tends to disorder. So in other words, the order increases. That is another way of putting it. I mean, disorder increases, I should say. This is what Mr. Boltzmann actually has shown. Okay. So that's actually the same way as saying the second law of thermodynamics. And this is where what it means, that the entropy, which is the measure of how much order there is in a system, increases, or lack thereof in this case, increases. So even living organisms observe this one in here, okay? And if you leave your room unattended, after a while you come find it in its complete, basically, disarray. This starts to decay on their own, okay? So if you wake up in the morning tomorrow and you don't do your room and you leave it like that, don't blame anybody. I mean, the entropy is going to take over, so you don't have to worry about it. So there is no need to worry about it, okay? Obviously, if you spend work to organize it, the entropy will actually decrease, but that's, you have to do it manually. You have to have something done to it to fix that. So your locker gets messier each week. In this case, the entropy of your locker is increasing. Okay, that is actually how the second law of thermodynamics can be put also. The net entropy of the universe is continually increasing. Okay. At some point, it may be increasing. Like, for example, organism looks like, for example, fixing itself and then getting organized. And, for example, a human being grows and becomes. But that is because there is energy intaken in this case. So there is an external process to help it get organized and to help it increase its temperature and to decrease its entropy. But in this case, it's really not spontaneously. Spontaneously, it's going to, the entire universe actually will see its entropy decrease in this case still, increase in this case still, because of the fact it takes energy from the environment to do that. So the universe will always see its entropy. The symbol for the entropy, by the way, is S. Okay, entropy. The change in entropy is always at best equal to 0, but that is an ideal situation, so-called the reversible process, but that is not always true. So it's always increasing in the universe. So again, that is the point of a lot of discussions, and there is a famous story by Isaac Asimov. Is it a Z, or I always kind of confuse his name? Did anybody read to him stories about the foundations and all of these things? Anybody? Yeah, it's an S. Asimov. Is anybody familiar with Isaac Asimov? He's got so many stories, so many books, actually. Okay, if you never read him, here's a story that you can read. He's got so many books that are about science fiction. He was a chemist, actually. He was not a, but he was also a famous sci-fi author. So the question that is the book that is worth reading in here, that is related to entropy, is The Last Question. As a matter of fact, he became famous for it. Wherever he went to, people ask him to tell the story, okay, of The Last Question. And if we have time, and I'm hoping that you guys can read it. Now, if you have strong faith in any religion, it doesn't matter which, you may refrain from reading this book, okay? I'm going to warn you about that, because it's going to shake your belief in God himself, okay? If you don't have any problems, then you can read it. or if you have strong belief and you think that your belief is strong, so go ahead and read it. If not, that is the word of caution that I'm going to tell you about that. Okay. Anyway, this is the chapter for 18. I combined chapter 19 and 20 together. They deal with waves and sound together. I'm thinking also to do the same thing for 21 and 22. 21 is so small, it's about musical things, that probably are going to combine it with 22. 22 is going to be far more important chapter for us from the next bunch of chapters because it deals with the, I mean, don't take me wrong, 19 especially is very, very important, deals with waves. 20 is an application of waves for the case of sound. 21 is even a smaller application of the two for the case of musical instruments. And if it's okay with you guys, because I've been thinking about this one for a long time now, I'm thinking to change careers, okay? And I'm going to confess that to you guys. I'm thinking to quit my job here teaching and teaching at all. And I'm thinking to become a musician. And I'm going to perform actually when we do the music in front of you guys, because I know how sound works. So I think I'm going to do it right. And I'm going to get your opinions about my performance and whether or not you guys should encourage me to do that or not. Okay. You guys understand? So when we do that, chapter 21, it's okay. So, I'm serious about it. Okay. So I'm hoping that you guys will be here when we do chapter 21, when we talk about standing waves. Okay. So that you guys can tell me honestly what you think about my performance and whether or not I should quit my job and become a full-time, basically, musician and go on tour and things like that. Then chapter 22, like I said, is very, very important too. Okay. Judging from my statement, it doesn't look like I'm going to be a successful musician because I'm going to chapter 22. Okay. So I see you guys next week. For those who are in physics 11, I'm going to see you later on in the day at 6 p.m. Okay. Thank you, Kyle. Okay. See you guys. Bye.